Okay, so it's my pleasure to introduce Koushil. I think a lot of you already know who he is. He's a faculty in mechanical engineering with a courtesy appointment in the Robotics Institute. He got his PhD from the University of Michigan and postdocs at Penn. His work lies in the intersection of nonlinear control and robotics, which explains why he can talk about legged systems and helicopter systems both in the same talk. If you look at his biography, there already is an impressive list of media appearance, media attention, and awards. You know, it's to the point where I'm starting to feel jealous. Thank goodness I have tenure. But Koushil, he's new to Carnegie Mellon. He's new to the Robotics Institute, and I thought what we would do is welcome him by making him give a talk, and then we'll all grill him. Okay, with that, please.
Yeah, thanks for such a wonderful introduction. So it's going to be hard to make the talk worthy of that introduction, so I'll give it the best shot. All right, so my talk today is going to be on nonlinear geometric control for highly dynamic robotics, in particular for legged locomotion and aerial manipulation. So my research is at the intersection of highly dynamic robotics and applied control, so it doesn't advance over there. Okay, there you go. So my research is at the intersection of highly dynamic robotics and applied control theory. So what I would like to do is, so to give you some motivation, so let me show you a couple of videos from nature. So these are biological creatures that move with great elegance, exhibiting high performance features such as high speed, ultra efficiency, super maneuverability, and extreme agility. So the first video I'm going to show you is a high speed chase. So a snow leopard chasing a mountain goat on extreme rugged terrain. So what you'll notice is none of these creatures miss a single step. They don't even slip. There is no machine out there that can match the performance that you see here. We don't even come anywhere close. So not to worry, the goat is not harmed. So I'm going to play it till the end for you to see the violent end. So it's good, right? So the next video I'm going to show you is the most fastest creature known to man. And this is not the cheetah, it's actually the peregrine falcon. So this bird can pull speeds up to 250 miles per hour, which exceeds the terminal velocity of a human in free fall. And this is the primary mode of attack for this bird. So it hits its prey at such high speeds that there's instant death. So if you're a prey, you don't see it coming, and it's painless. So what's important is this bird can pull out of such high speeds extremely well. And once again, there's no machine out there that can match such a capability. So my goal is to endow machines with such capabilities. And this highly dynamic robotics are actually needed in society, especially when you want to perform in unstructured, remote, and unsafe environments, and applications where time is of essence. So disaster response, first response, and you want to create smart bionic devices. So these are not only needed in society, we also have the technology, or will have the technology in the very next few years to create such machines. So we are making great technological advances in mechanism design, sensor, actuator, power, and also computing technologies so that we can create these machines. One of the most important ingredients that's missing to make this behavior possible in practical life is the system science. So we don't have the math tools to understand and to design controllers to make these systems behave in the real world. So you can build mathematical models for robots, but it's very hard to characterize their interactions with the ground, the aerodynamic effects, and we're still not there yet. So it's a very interesting problem, and it's also a challenging problem because of these reasons. So these systems are typically characterized by high degrees of freedom, and not all of these degrees of freedom are actuated. So you have very few actuators, so you have high degrees of underactuation. These robots typically have nonlinear dynamics, and when they interact with the ground, you have hybrid dynamics, so which makes it a very hard problem for control. And the systems operate in regimes which are hard to model and also stochastic. So think about aerodynamic effects, think about interactions with the ground. So you can build models for this, but they're very far away from reality. And the controllers you design have to be embedded on real-time controllers. So you have hard real-time constraints. So that's another constraint on your control design. And more importantly, you have to design controllers that can preserve the natural dominant dynamics so that for reasons of energy efficiency. So how do you design a controller that can handle all of these things for a certain class of systems? So for today's talk, I'm going to talk about two problems. So one is on dynamic legged locomotion. The second is on dynamic aerial manipulation. And both these problems share common themes: high degree of freedom, high degree of underactuation, nonlinear hybrid dynamics, and we're trying to design controllers to create dynamically agile motions. So the first problem, this is MABEL, a planar bipedal robot. Here's an actuator. There's a cable transmission that connects to various pulleys. There's a cable differential, and finally the leg moves. It's a complex mechanism. This was designed right here at the Robotics Institute about 5 years ago by a grad student, Jonathan Hurst, who was sitting here several years ago. So this robot arrived in my lab as a bucket of parts. So my goal was to take this complex mechanism and make it exhibit highly agile motions such as this. So this is dynamic running, played back at a quarter speed. So great ground clearance, good flight times. And we're going to talk about how to design controllers to make this possible. The second problem I'm going to talk about is on aerial manipulation. So I stole a quadrotor from Nathan's lab. Thanks, Nate. And this is a little bigger than I expected. So the goal is to have a quadrotor with a cable suspended load. So all of you know a quadrotor is an underactuated system. So to this system, let's add in a cable suspended load. There's no actuation here. You're adding additional degrees of underactuation. And the goal is to design a controller so that you track an arbitrary trajectory for the position of the load. And you can imagine if someone gives you a trajectory that's circular for the load, and they ask you to track it slowly, you would imagine the quadrotor to fly around right above that trajectory if it's a slow trajectory. If they give you the same exact trajectory, and now you want to go around faster, so there is a case when the quadrotor is actually moving very little, and you're still following the same trajectory. So how do you design such a controller where actually the dynamics evolve on a manifold? And more importantly, let's say you start off with the initial condition where the quadrotor is inverted, your load is inverted, and there's a huge error in your load position. So how do you design a controller that can recover from anywhere in your state space? So you are looking for almost global stability properties. So the rest of my talk is structured as follows. So I'll talk about dynamic legged locomotion, dynamic aerial manipulation, and give you some concluding remarks. So there are several potential applications which are amazing for legged locomotion. So some of them are you can access terrain that's not accessible to wheeled robots, but more importantly, you can design smart bionic devices to give mobility to people. And you can also create devices, exoskeletons, that give you superhuman strength for rescue workers. You can also use this to design transportation mechanisms that are highly efficient over extreme terrain. And this has several challenges. Some of them are similar to what I showed you before. But the main thing here is you need to design controllers that create periodic orbits, because walking and running motions are periodic. And you need to design a controller that creates a stable periodic orbit. So this is harder than creating a single equilibrium and stabilizing to that equilibrium point. So it's a challenging problem, but this hasn't stopped researchers from attacking this problem. So there's several approaches for walking. So the most dominant one is the one pioneered by Honda. So this is 16 years of evolutions of Honda's Asimov. And it uses a control method called ZMP, the zero moment point. And the goal is just to keep the center of pressure within the support polygon. So you get walking gaits, which are very robot-like. They're not agile, they're not energy efficient, and they're not robust. The second set of approach is pioneered by Mark Ribot back here in the 80s at the Robotics Institute. And he could realize extremely agile motions, but the problem is these were not always transferable to complex mechanisms, so you needed simple dynamics. So another approach was pioneered by Ted Magyar, an aerospace engineer. So he asked the question, why cannot we design, airplanes can fly with no power, no actuation. Why cannot you design walking and running mechanisms that can move around with no actuation, no power? That's actually possible. So you have passive dynamic walking, passive dynamic running. So these are systems that can walk and run down gentle slopes. So the energy lost at impact is regained by going down a slope. And you can also walk on flat ground if you put in small little actuators, either at the knee or the hip. So it's minimalistic actuation. So this class of robots are extremely energy efficient, but they're not robust. So small little perturbation on the ground and they're flat on the ground. You cannot change their walking gait. So you have a class of controllers. So this can walk, but it's not robust, it's not energy efficient, not agile. Agile walking motions, energy efficient motions. Finally, there's one class of control design called hybrid zero dynamics, where you can design walking gaits that are robust, agile, energy efficient, and so on, all of it together. And making a robot run is extremely hard. So early approaches assumed that even if a torso was present, the torso dynamics was not significant. So the hip joint was coincident with that of the center of mass of the torso, so that when you move the leg, it doesn't affect the torso at all. In recent years, we have running on more complex mechanisms, but the achieved running is impractical. So you have only a few millimeters of ground clearance, and the flight times are tens of milliseconds. So a small little perturbation, and the running is not practical. So in 2004, so the French bipedal robot called Rabbit, it exhibited running motions, but it was not sustained. It could only run for 6 steps. So what I'm going to show you today is the control design to create running motions on systems with non-trivial morphologies, especially with legs with knees. So first, to give you a model of this machine, so this is a planar robot. So it has 5 links, and 4 actuators, so 2 at the knee and 2 for the thigh. The key thing is it's got point contact with the ground, so there's no feet. So you have to truly study dynamic stability. And more importantly, this has compliant elements, springs, so that you can store the energy at impact. And you can return that into the gate to create energy efficient gates. So the transmission mechanism for MABEL is fairly involved. It has 3 sets of cable differentials. So what this entire mechanism does is the following. So it creates a spring and a motor in series, and it places that along a virtual leg that connects from the tip of the toe to the hip joint. And there's one actuator that controls this leg length, and there's another actuator that controls the angle of this leg. Now the dynamics for running is hybrid, so you have one continuous time dynamics for the stance phase, and you have a transition to another continuous time dynamics, and then when you have impact, you come back to your stance dynamics. So the controller you design has to be for this hybrid dynamics. Yes, sir.
Question. So for your leg model, when you have that series elastic, actuator, your 2 degrees of freedom are the length of the resting. You're altering the length of the resting, length of the spring, and then the angle of the leg. Is that right?
So we have 3 degrees of freedom. One is the length of the leg, and one is the spring itself. So that's an unactuated degree of freedom.
Okay.
So you have 2 degrees of freedom. So one given by this and one given by this, and one is the angle. So you have 3 per leg.
And I was just curious how that mapped onto the two links that you had allocated for the leg in your stick figures. In other words, I was just trying to resolve.
So a linear combination of these two would give you the length of the leg.
Okay.
Or would give you the knee angle.
Okay.
And this actuator would give you the angle of the leg. Okay, so the controller I'm going to present to you is something called hybrid zero dynamics, and it's based on virtual constraints. And to understand virtual constraints, let me show you a kinetic sculpture. It's by Theo Johnson. So here's a mechanism which has hundreds of legs, hundreds of degrees of freedom, but all of them are coupled using mechanical constraints through a central crank angle. So as the crank rotates, here's a simulation, you can take a walking gait. So a simple mechanical constraint. And this mechanical constraint can be expressed as the following. So if you have the crank angle as the angle theta, so all the joint angles are now a function of the central crank angle. And this expression gives you a mechanical constraint. Now if you want to design a walking gait that's slightly different, so you want to take a longer step or a higher step, what Theo Johnson has to do is he has to pull out his hacksaw, take off some of those mechanical constraints, design another one to replace that. So that's possible, but it's very hard. Instead, what we can do is we can programmatically change these constraints using virtual constraints. So what you do is take off these mechanical links, introduce actuators at the joints and encoders, and express the same equation now as an output function y. And use feedback control to drive this output to 0. So what you're doing now is you're realizing these constraints virtually through feedback. And this has several benefits, so you can change these constraints on the fly, and we'll see how that's possible. So the first question is, how do you apply this to a legged robot? So what is your crank angle? So if you take the angle of this line with the ground, and you parameterize the thigh and the knee angles as a function of this theta, you can actually realize a walking gait. So this is theta here, these are your actuated coordinates, and you can generate these trajectories so you take a step. So what you're doing here is you're building in reflexes into your system. So if someone were to come and push your robot ahead faster, so theta would increase faster, so you would go along this axis faster, but your swing leg would come ahead to catch itself from falling. So you're building in reflexes into your system. Now all this can be expressed mathematically very well. So this is one slide that summarizes everything. So what you have is a high degree of freedom hybrid system. And using virtual constraints, you're reducing it, in this case, to a single degree of freedom hybrid system using dynamic feedback. So the dynamics on this surface would be the dynamics of this angle theta. And you're using an actuator, one actuator per each output to enforce this virtual constraint. So what your feedback control is doing is two things. So one, you're creating a manifold or a surface in your state space. And that surface is characterized by y equivalent to 0. And your controller is driving the state onto the surface. So once you're on the surface, you're invariant, so you don't come out of it. The second thing you're doing is every time your foot hits the ground, you have an impact. And there could be a discrete transition of your state. So you need to make the surface invariant to the hybrid impact. So you combine both of them together. So this is called the zero dynamic surface. And you get hybrid invariance and you get hybrid zero dynamics together. So to design these virtual constraints, we have 2 degrees of freedom. So one, we can choose the variables on which to impose the constraints. So the one here could be the thigh or the knee angle or any nonlinear function of your degrees of freedom. The second is you can choose the shape of your constraints. So this is how you want your constraints to evolve. So for instance, for MABEL, if you choose this as a variable on which to impose your constraint, then the dynamics on your surface would be that of an inverted pendulum whose length and inertia vary as a function of theta. The problem with this is it's not energy efficient because your controller will try to cancel out the spring. Whereas if you change your virtual constraint so that you place a constraint on this part of your leg length and leave the spring free, then your spring moves onto your zero dynamics and you get a compliant system. So the dynamics on this surface are compliant. So you're preserving the spring so that you can do energy efficient gates. So what about the shape of the constraints? So if you want to hold this actuator constant at impact, so the spring would compress, it would store all the impact energy and then return it to your gate. So this way you can get energy efficient gates. And you have other constraints on the torso angle and the swing, leg length, and your leg shape. And you use optimization to design these constraints for a walking gait. So the choice of your virtual constraints can make your zero dynamics compliant. And the choice of the shape of these constraints can utilize this compliance effectively. So one interesting plot here is if you design your gates effectively for energy efficiency, so this is a plot of instantaneous power at your knee. So the red is the total instantaneous power, whereas the black is the one that's being supplied by your actuator. The difference is the energy that's saved because of your gate design. So you get very energy efficient gates. And in fact, if you were to use a metric that's used in the light community called the specific cost of mechanical transport, this is essentially the positive work done by your actuators, normalized by the weight of your robot and the distance traveled. And you can see that Honda's ASMO is 1.6, and MABEL is about 15 times better. And all these other robots here are created specifically for energy efficiency. Whereas here on this robot, you can design gates that are robust, are more agile, you can have running gates. So we're just a factor of 2 away from that of a human. So you can design these nonlinear controllers to get extremely energy efficient gates. And how do these things look like? So here is a very slow walking gate. You'll always think it's falling backwards. And then here's a really fast walking gate. You can take the same controller and you can make it walk by adding legs to this robot. So here you'll see a heel strike, a flat-footed face, and then a toe off. And just for comparison, so here is a cameraman from Discovery, and you don't know who's walking better. And you can also have robust walking. So here is MABEL walking, so it has no knowledge, it has no camera, so it has no knowledge of these boards. Each of them are about 1/2 inch to 1 inch thick. So what you'll notice here is, so MABEL will place a foot right at this edge, and it'll cause one of the boats to slip. But because your controller has reflexes built into it, it makes your swing foot come forward automatically to catch itself from falling. So here's the same thing in slow motion. So this was about 2.5 inches. Now we've gone about to 8 inches. So you can walk blindfolded off a sidewalk and still continue to walk. So how do you drive this output y to 0? So until very recently, there have been only 3 kinds of methods. So I won't go into the detail. But now we have another one based on control Lyapunov functions, which increases the family of controllers for hybrid zero dynamics to infinitely many. A control Lyapunov function is very simple. I'll explain that in a moment. But what you can do with this is now you can impose torque constraints. So how do you continue your system to walk when your battery is dying? So you want to impose torque constraints on your system so that this is your nominal walking periodic orbits. But as you increase your torque constraints, your performance degrades, but the performance degradation is slow, and you still continue to walk. So you maintain your walking objective. So what are control Lyapunov functions? They're very simple. So let's say you have your system dynamics x dot equal to f of x plus g of x u. And you have a scalar function, v of x, which is positive everywhere except at the origin. and you want to make your system go to the origin. So one way to look at it is through a Lyapunov function. So if you take this v and look at the time derivative, it's dv by dx times x dot, which is f of x plus g of x u. What you want is you want v dot of x to be negative, so that v decreases. And here we have a parameter u. So can we use u, or does there exist a u so that v dot is negative? And if that is true, then v is a control Lyapunov function. But you can do something more than that. You can actually make v dot less than minus a constant times v, which then makes v go down exponentially. So if there exists a u such that this entire expression is less than this, then you can have exponential convergence. So how do you choose such a u? And you can choose such a u by posing a simple quadratic program. So minimize u transpose u, subject to v dot plus cv less than equal to 0. And now in this quadratic program, you can introduce torque constraints. So suppose you were to relax this constraint. Instead of 0, you have a positive d. Then you can introduce torque constraints u min and u max. So now you can let your performance degrade gradually. So the next experiment I'm going to show you demonstrates this controller. And this experiment was done remotely. So I was 600 miles away controlling this robot over the internet. So we used remote desktop, Google Hangout, and lots of other things. But you can do this real-time control over the internet, and it's possible. So what happened is we switched from the regular walking gait to that with torque saturations, and you still have walking. So now I'm going to switch from walking to running. And so we've designed walking gaits where the spring compresses, decompresses, stores energy as part of your gait. But the problem is the following. The spring compression and decompression happens in 100 milliseconds. And this time period is a characteristic of the weight of the robot and the spring stiffness. So for running, 100 milliseconds is too small of a time to regulate the torso position during stance. So you want to increase this a little bit. So one way to do that is to reduce the spring stiffness. But the spring stiffness appearing at the leg is nonlinear with the spring stiffness that's being used here. So in fact, it's a softening spring. So if you make it softer, the leg would just collapse. So if you look at towards biomechanics for inspiration, so here is a very famous experiment by Monica Daly. So this is the guinea fowl that's running, and this is a sheet of paper. So what the fowl doesn't know is this is going to give away. But birds are very good at running. So if you look at the center of mass trajectory, even with such a large perturbation, there's no variation in the trajectory. And what they do is they vary the stiffness of this leg to achieve this. So can we do the same thing for robots, in particular for MABEL? So we had a virtual constraint on this part of your leg. Now if you remove this virtual constraint, then the dynamics on the surface also has an actuator in series with a spring. So you can effectively modulate the compliance of your leg using the actuator. So if you do this, you can design periodic gates for running. The only problem is all the periodic gates that you design are unstable. So you need an additional controller to stabilize these periodic orbits. So you have a continuous time controller that creates this surface in your state space. And then you have an additional controller that smoothly morphs the surface at each step to stabilize your periodic gate. So you put all these together, and here is how the running motion would look like. So it's got the torso is upright, it's got good flight times, and you think we're ready to deploy this on an experiment. So the only problem is this control design was done on a simple system. And the simple system assumed the ground was rigid. It assumed the cables in your transmission do not stretch. It assumes the robot was actually planar. Whereas in reality, the ground is compliant, the cables stretch significantly. The cables are guaranteed not to stretch. They're aircraft grade from the manufacturer, but they stretch significantly. In fact, for the experiments I'll show you, over 70% of the motion in the leg is because of cable stretch in the knee. And the robot moves on the surface of a sphere. It's not planar because of this boom. But since you have an actuator in series with your spring, you can cancel out this cable stretch. And you get the very first experiment on running with this controller. So here's MABEL transitions from walking to running in a single step. It's taking very good running steps, but then it fails. So the failure mode is obvious. So if you look at this running gait, the controller is not the best. The swing leg is oscillating a little bit, but you can modify that to change it out. But the failure mode is obvious. The leg just slips on contact with the ground. So you think this is an easy thing to fix, right? So the next 2 months, all the experiments I did were the following. So if you look closely, if you look for long enough, you'll see the seasons change in the background. No, I spent some time thinking about what I would do in my next life after I was done being a control engineer. But if you come back and see, what is happening, what's wrong here, the problem is the model for the ground is actually not the best. So the best model that you can obtain for the ground is very far away from reality. The ground model varies as you go around the floor. And more importantly, there's a point contact with the ground, so the traction is very less, so it's very easy for the robot to slip. So once you realize that, how do you increase traction? So one way is you can put in passive feet. And you can take the same running controller implemented on this system. It's very crazy looking running gait. But once you get it working on this, now you can get it working on a point foot too, because your controller was designed for the point foot in the first place. So these are anti-slip mats, the ones that you'll probably see in gymnasiums. So they're not compliant, they're pretty stiff. So once you have those, you can design, so you can implement the same controller to achieve dynamic running motions. So the top running speed is about 3 meters per second, which makes MABEL the world's fastest running robot with knees. And you get flight times of about 100 milliseconds and ground clearance up to 3 to 4 inches. So it's truly running, truly dynamic running with good ground clearance and good flight times. And you'll notice the robot tends to slip over there, but the controller is robust enough to recover from that every single time. So here's the slow motion. So it looks very lifelike. So it's dynamic running here in action. So what I've shown you for leg locomotion is the following. So I've shown you a formal control design for systems with knees, so where you have a non-trivial morphology. And this gives you an analytical proof of stability and also an experimental validation. So stable, efficient, fast walking and stable, fast running can be achieved on MABEL with this controller. So now I'm going to switch to aerial manipulation. So we're going to go from ground to aerial robots. And once again, we have similar themes. So high degree of freedom, high degree of underactuation, nonlinear and hybrid dynamics. And we're trying to achieve dynamically agile motions. So to recall, so we're trying to design a controller to track an arbitrary trajectory for the load. And the system is highly underactuated. So it has 4 actuators, 8 degrees of freedom. And you want to recover from any state in your state space. And this is also an important problem because you can use this for load transportation, for rescue operations. In fact, I have an example of a rescue operation. So this is a true life story. It's from episode of I Shouldn't Be Alive on Discovery. So 2 climbers, Swiss climbers, they climb up the Alps and they get stranded over there because of heavy snowfall. There's complete whiteout and they cannot come down. So the next day, the snow clears There's a rescue attempted. Surprising, the pilot spots the climbers here, and they attempt a rescue operation. But the problem is, the pilot is not able to stabilize the position of this rescuer who is suspended by a cable. And the rescue is aborted. And the next time they can attempt this rescue is 3 days later. And one of this climber loses his life. The other climber loses both his feet, both his arms. It's a sad tragedy, which could have been easily avoided if you had a controller that could stabilize the position of a cable suspended load. So we have similar challenges to the ones I've presented before, but now the dynamics evolve on manifolds. So I'm going to show you why that is true, and you have to design controllers that respect this evolution of the dynamics on the manifold. And you want to design controllers that give you global stability properties. So aerial manipulation has been attempted by several researchers. So the most predominant ones are listed here. So early manipulation attempted having a gripper on your quadrotor. But the problem with this is having a gripper increases the inertia of this entire system. So it makes the system very sluggish. So one way to handle that is to have a cable suspended load where you still preserve the agility of your aerial robot and still get load transportation. But most of the early research was on quasi-static motions. So where you assumed the motion was slow enough, so the inertial effects are not part of your control. So the first time the control was used was to cancel out any kind of oscillation. So you have an aerial robot with its cable suspended load. So you want to move, but you want to cancel away all kinds of oscillations. And that's what's usually used in cranes when they're transporting loads. So you cancel away all oscillations and you move slowly. What I want to do is the opposite. How do you move where you actually increase the oscillations so that you get dynamic motions? And I'll show you an example of this in a moment. So until very recently, this was the state of art in object retrieval using aerial robots. So you take an aerial robot, hover over the object, slowly go down, pick up the object, come up. In contrast, what birds do is very different. They have a high-speed approach, and they have a high success rate of grasping their prey from water, from the ground. This is how they steal your lunch if you're sitting outside. So how do you make aerial robots do the same thing? So I'm going to talk about the math and the control for this in a moment. But what birds do is the following. They actually swing the legs backwards, so they reduce the relative velocity at pickup to almost zero. So if you give an aerial robot an actuated appendage, you can do the same thing. So you can reduce the relative velocity at pickup, so it's almost like you're hovering, but you're moving really fast. And you can achieve this up to 2 to 3 meters per second. So this is a slow motion at 2 meters per second, and then we're going to show you at 3 meters per second. So this is with an actuated gripper. The problem I'm trying to study is one without an actuation. So for this system, the dynamics are also hybrid. So you have a continuous set of dynamics when the cable is taut, and when the cable becomes slack, when the tension goes to zero, the dynamics switched over to another set of dynamical equations. So more importantly, the dynamics actually evolve on manifolds. So for this system, so the orientation is given by a rotation matrix, which evolves on SO3, the space of rotations, yeah. And the suspended load evolves on the surface of a sphere. So the developing dynamical equations directly in this set of coordinates is actually very good because you get compact expressions for the dynamics, they're singularity free, and they're valid globally. And to do that, you should use the calculus of variations. But the key thing here is the variation that you take, delta Q, has to be on the manifold. And if you do that, delta Q then becomes a variational vector field. And you can use the Lagrange-D'Alembert principle to get the dynamical equations. So for this system, if you were to use roll pitch yaw for the quadrotor and another two rotation angles, the dynamical equations will be really complicated. Whereas if you do this, you get the following equations. They're very compact, they're valid globally, there are no singularities. So what's key here is the quadrotor attitude dynamics. So the quadrotor attitude dynamics is totally decoupled from that of the load. And the gravity does not affect the load attitude dynamics at all. And what that means is whether you have the load suspended or whether you have an inverted pendulum on a quadrotor in the same set of dynamics, the gravity does not affect it. And more importantly, the load attitude is decoupled from the load position. So we'll use all these three aspects to design a controller. And before I do that, I'll talk about designing nominal trajectories which are dynamically feasible. So the key thing here is this system, a quadrotor with a cable suspended load, is differentially flat. And what differentially flatness means is the following. So if I have a set of outputs, I know everything about the system from that output and its higher order derivatives. So for this system, if someone gives me the load trajectory as a function of time, I know everything about the system. So I know what is the quadrotor position, I know what is the thrust required for the load to follow this position, I know what is the moment to be applied to the quadrotor. And to see that, you can take the time derivative of this load position, and you get the acceleration from which you know what is the force to be applied. And this force has to come from the tension in the cable. So you know the vector for your cable, so you know the quadrotor position. Now if you take the time derivative of the quadrotor position, you get the acceleration and you can compute the thrust required to move along that. And you also know the orientation from the yaw. So you can also compute the rotation and the moment. So you know everything about your dynamical system just from the load position and the quadrotor yaw angle. And what's interesting is you can extend this differential flatness to hybrid systems. So you have a hybrid system. So just by planning out this load trajectory, you can exactly predict when the system dynamics will switch from this set of dynamics to this, and from here back to there. So you can plan out these hybrid trajectories that switch between different sets of dynamics. And you're doing no integration, you're just planning out in your flat space rather than in your state space. And coming back to this problem, so you suppose this is your load trajectory, the blue line. And if you have to track this load trajectory at slow speeds, from this differential flatness, you get the desired quadrotor position. So this is the quadrotor position to track this trajectory at slow speeds. Now if you increase the speed of this load trajectory faster and faster, the quadrotor trajectory at some instant just becomes almost vertical. If you go beyond that, which is the natural frequency of your system, then you get really aggressive motions for your quadrotor. This is the same plot in different views. So you have the nominal trajectory, so now you want to design a controller. And once again, the dynamics evolve on the manifold, so SO3 cross S2 cross R3. And designing a controller such as even a PD control on a manifold is not trivial. So for instance, so let's take the sphere. So if you have the current configuration given by a point on your sphere, Q, and then you have the desired configuration, QD, another point in your sphere. So even the position error is not trivial. It's not just Q minus QD. So there's a configuration error function that you can choose, which could represent either the geodesic or the chord length. And if you want to compute what is the velocity error, that's even harder. So for instance, the velocity, the current velocity is the velocity in this vector space. And the desired velocity is the velocity vector in this particular vector space. So two different vector spaces. And you cannot compare the vectors, two vectors in two different vector spaces. So what you need is another function that maps this vector back to this vector space. And there is a compatibility condition between these two, so that your PD controller is now of this form. And the complexity of this controller is dependent on your choice of these functions. So even PD control on manifolds is non-trivial. So for this system, you can design an inner-outer loop controller, a geometric controller. And the control equations itself are fairly compact, so they're not very important for the talk. The key thing here is if you just change the sign of this controller, the same controller that works for a suspended load will now work for an inverted pendulum. So you can not only balance your inverted pendulum on a quadrotor, you can follow any arbitrary trajectory for the tip of the inverted pendulum. And just to show you a simple animation, so here we start off with an initial condition with the quadrotor totally inverted, the load inverted, and there's a huge error between the current load position and the desired load position. So the red gives you the desired load trajectory. So the quadrotor, the controller causes the quadrotor to flip, it causes the load to flip, and then you have exponential convergence to the desired trajectory. And if you think this is easy, the same controller would also work for an inverted pendulum. So you could start with the quadrotor inverted with the pendulum hanging down, and the goal being to make it the pendulum balancing inverted while tracking a trajectory for the tip of the inverted pendulum. So once you can solve this particular problem, so what do you do if your load is very heavy and cannot be carried by a single quadrotor? So the natural extension is to have multiple quadrotors carrying a point mass load, or if you have a rigid body load and you have n number of quadrotors, you can look at this problem too. So these problems become harder because your number of degrees of freedom is now a function of n. The number of degrees of underactuation is also a function of n. And the key thing here is you can actually show that this system is also differentially flat, which means you can design nominal trajectories for the system just in your flat space. You can also design nominal trajectories for this system using your flat outputs. But more importantly, these are differentially flat hybrid systems, which means you can plan trajectories which take your system dynamics where all the cables are taut, and you can predict exactly when your system dynamics switch to one of the cables going slack, and you can have another cable going slack, and so on. And this is all motion planning which are dynamically feasible for hybrid systems. So once you have those motion plans, the next thing is to design controllers to follow these trajectories. So this is a simple representative experiment. So we have 3 quadrotors, and the goal is to follow a trajectory in the vertical plane for the load. And the speed of following this trajectory changes. So initially you're going slow, and then you start going faster and faster, which makes the quadrotor, this particular quadrotor trajectory, change drastically to this point. So here's an experiment that will show that. So it starts off like a boring experiment. So you have 3 quadrotors on the top, and you're trying to follow, you keep the load horizontal and follow a trajectory in your vertical plane for the center of mass. So with time, the frequency of this load trajectory increases. So if you look at this quadrotor cable, you'll see the oscillation increase dramatically with time. So initially it's almost above the load, but then now this angle changes quite a bit. So this was a representative experiment. So the goal is to repeat this with multiple quadrotors. So for comparison, if you want to take the dynamical effects into account, you would get this red load experimental trajectory, where the load would deviate quite a bit from your nominal trajectory. So what I've shown you is a control design for achieving avian-inspired dynamic object retrieval, a way of designing dynamically feasible trajectories for this complex systems using differential flatness extended to hybrid systems, and also a geometric controller which controls the system to give you global stability properties. So in conclusion, I've shown you my research specifically on dynamical leg locomotion and aerial manipulation. And I would like to acknowledge my collaborators and my current students. So thank you for listening to me. I'm happy to take questions now.
So I had 2 questions. So I'll just go with the first one. So when the cables, when you were playing just for a single robot with one cable, not the hybrid system. I was just wondering if you always modeling the cable as if it was just a rigid bar because the cable is always taut, or is there something, or is there some other dynamic effect going on where the cable can become slack or maybe stretch and contract a little bit?
So we have a hybrid system, so you assume the cable is taut. For that you have a set of dynamical equations.
Okay.
Then when the cable is slack, you have another set of dynamical equations. And then you can plan trajectories that go from one set of dynamics to another one.
And when it's taut, you just treat it like a rigid bar.
So you treat it as a massless rod.
Massless rod, right?
Yeah.
I was just wondering if there was some are you introducing dynamics into the cable as well that can affect motion? Maybe you're not. So I get the hybridness. So what you do?
So you have a transition map here. So every time the tension gets re-established, it's actually treated as an impact. So you have a discrete change in your velocities.
So there's something more complex going on when the cable's in tension is with
On a physical system?
Yeah.
So the cable could actually stretch. So it depends on how stiff your cable is.
And can the cable somehow inject some sort of disturbance into the quadrotor?
So on a real system, the cable could be treated as multiple links with mass, whereas we assume it's a single link without mass. So the cable can actually be curved. So you can have lots of other effects which are not modeled here.
And then my second question, with the figure on the next slide. So again, in red, you're going around nice and slow, and then you have these nice things that are diffeomorphic to circles, I guess. And at some point, you inject a kink into the trajectory. Is there Is there like a little critical point in there, or is there a point where things just change?
So this is X versus Z or something. So this is a quadrotor position that goes this way.
Right.
So if you look at this,
when you go from red to brown, is there this one point where is it collapsing to a point, or is a kink first forming? Like what's the trajectory look like just before the last red and the first brown?
so if you look at it, it's looping around. So that looping thing reduces, then it just becomes a single point over there. So it's not a singularity. It's just the way the trajectory changes in X versus Z.
So you're saying the loop comes down to a little kink?
So the loop cancels out. So this is so these are the different frequencies for the tracking the same blue trajectory.
Okay, thank you.
Yes.
So for these, I guess for both cases, how critical is it that you have a well-identified system? And how does that impact the robustness of the controller?
So for the control design, you assume a set of system dynamics. So for instance here, so I assume the cable was suspended at the center of mass of the quadrotor, which would be really hard to do on a physical system. So the cable dynamics would affect that of the quadrotor attitude dynamics. So that's not modeled here. But you need to think about those things when you're physically implementing it on an actual system.
I mean, like the mass and the inertia, all the parameters of the model. Do you have to do a very detailed system ID in order to
How robust is the control design? So for the control design for the legged robots, so what I typically do is I design a controller, validate it on the best model that I have in simulation. Then I do a parameter perturbation. So I change the mass, I change the inertia of different things, and see if the controller is still robust to that perturbation. And if the answer is that it is true, then only then implement it on the experimental system.
So that's part of the controller design is
Yes.
an iterative process.
So you can test all that out in the simulation. But there are still a few things that you do not account for instance, the ground model. That's pretty hard.
You're using optimization to design the controller.
So for the leg robot, I use optimization to design the gates. Yes. Yes, Nate.
as you're developing these multiple cable slack phases, how would you incorporate time delays?
How do you incorporate time delays?
You assume that you have a very good understanding of the slackness of the cable. But if you were out on that mountain trying to use multiple vehicles to save an individual, there's a certain assumption of how quickly those different vehicles can talk to each other. It seems like you could be entering in and out of different types of slack phases at a high frequency. I wonder how that would impact it.
So you need to be able to detect when the cable goes slack. And so right now I don't have a control design for the multiple quadrotor case as yet. So I'm working on it. But that control design would be centralized. So you still would have this delay. So I'm not sure how to address it right now. But if you're able to design a controller that gives you global stability properties, then it doesn't matter on these perturbations. So you have a controller when the cable is taut, you have a controller when the cable is slack, and both of them give you global stability properties.
For the centralized system.
For the centralized system. If you had such a controller, then that controller would take care of it. But if you didn't have a globally stable controller, then you would have to address these delays somehow.
So if you wanted to take this outside of the icon, you thought about what would have to change?
So you need some kind of sensing for the load position. So either with respect to the quadrotor, so that you can compute your quadrotor ELQ, the angle, and you also need some way to find out when this transition happens. So you can do that either using an optical sensor, a camera on the quadrotor looking at the load, or a tension sensor in the cable.
So in hybrid systems, chattering because of time delays is a concern. States. And a misunderstanding of that state. I'm just wondering if that will greatly impact performance in terms of the stability of those.
So there's a lot of chattering for hybrid systems, that's true. But there are control designs that give you Zeno equilibrium, so where the chattering dies down to zero exponentially fast. So if you can design such a controller, then that'll be taking care of it.
Do you have any more questions for our speaker? All right, well, let's thank him for coming.